Generate responses from the current policy. Score them, reward model minus KL penalty. Estimate advantages. Run the PPO update. Then loop. The run episode method does exactly that and then logs the mean reward, the mean KL, the response length, and the loss pieces before handing the summed KL to the adaptive controller. Seeing it written as 4 clean steps is the thing to carry into an interview, because that is the answer to walk me through the training loop. When the training run is assembled, the notebook prints a memory check, and that is not just decoration. With Tiny GPT-2, the 4 models fit in about 2 gigabytes and you barely notice. But this is the exact spot where RLHF gets expensive at scale. You are holding the policy, a frozen reference, a frozen reward model, and a value head all at once. At 70 billion parameters, those copies in half precision blow past half a terabyte before you even count activations. This 4-model memory problem is one of the defining engineering pains of RLHF. The real test is qualitative. They take the same set of prompts and generate from 3 models side by side, the raw base model, the supervised model, and the final RLHF model. You can literally read the progression. The base model rambles or drifts off topic, the supervised model answers in the right format, and the RLHF model is more on point and helpful. This before and after is the most convincing thing in the notebook, because numbers can lie but reading the actual output side by side does not. Then they quantify it. They score every model's responses with the reward model and compute pairwise win rates, how often RLHF beats supervised, how often each beats the base. You would expect RLHF to win most often against supervised, and supervised to win against base. One honest caveat to keep in mind, though, the reward model is also the thing RLHF was trained to maximize, so a high score by its own judge is encouraging but not proof. That is precisely why you still read samples and, at scale, run human evaluation. The dashboard plots the whole story, and learning to read it is half the job. The mean reward should climb and then plateau. The KL should rise because the policy is genuinely changing but stay bounded because the leash is holding. Entropy should drift down slowly as the model grows more confident. Response length, policy loss, value loss, and the adaptive beta all get their own panels too. A healthy run is reward up, KL gradual, entropy gently down. Anything sudden or runaway is a warning sign you want to catch early. Interviews love asking which hyperparameters actually matter. The notebook names 3. The KL coefficient controls how close you stay to the reference. Too low and you get reward hacking. Too high and the model barely moves. The learning rate, too low and convergence crawls. Too high and the KL explodes. And the batch size, bigger, gives a cleaner gradient estimate and more stability, which is why real runs push it as large as the hardware allows. If you can speak to those 3 and their failure directions, you sound like you have actually run this. Now the failure modes, because this is where interviews get serious. Reward hacking is the big one. The reward model is only an imperfect proxy for what humans want, so if the policy optimizes too hard, it finds the proxy's blind spots, responses that score high but are actually worse. The tell is reward climbing while the KL diverges and entropy drops, and sampled outputs quietly getting worse. The paper to name is Gao and colleagues on reward model overoptimization, which showed the proxy score keeps rising while true quality follows an inverted U and starts falling. The second failure is mode collapse. The policy converges onto one type of response for every prompt, and diversity dies. The signature is entropy dropping sharply while reward plateaus. You diagnose it by generating several responses to the same prompt. If they are all nearly identical, you have collapsed. The fixes are to raise the entropy bonus, ease the KL coefficient down a touch, or bump the sampling temperature. It is the model getting lazy in a different direction, betting everything on one safe answer. The third failure is KL explosion. The KL grows without bound, often exponentially, and the model drifts so far from the reference that it becomes incoherent. On the plot, the KL shoots up and then reward and everything else go haywire. The fixes are to lower the learning rate, raise the KL coefficient, lean on the adaptive controller, and critically, check your log probability computation for bugs, because a subtle indexing error in the ratio is a classic cause. The notebook even draws stylized healthy, hacking, and exploding curves so you can recognize each shape on sight. Now the system design teaser. How would you scale this to a 70 billion parameter model? The first wall is memory. 4 models at that size is hundreds of gigabytes. The answers: share the transformer backbone between policy and value, which we already do. Train only low-rank adapters with LoRa instead of full weights. Offload the frozen reference to CPU and bring it over only for the KL computation. And quantize the frozen reference and reward model down to 4 bits, since only the policy needs full precision. The second wall is compute, and the surprising truth is that generation, not the gradient step, dominates the time. Every PPO step needs the policy to generate full responses, and generation is autoregressive, strictly one token after another, while the update parallelizes across all tokens at once. The fixes are optimized inference engines like VLLM, with continuous batching, speculative decoding with a small draft model, asynchronous pipelines that generate the next batch while training on the current one, and simply capping the response length. If asked what is hardest about scaling RLHF, this is the answer. The third piece is the distributed architecture, and the key insight is to separate generation from training. You run a pool of generation workers holding inference copies of the policy, the reference, and the reward model, and a separate pool of training workers holding the live policy, the value head, and the optimizer states. The generators produce prompts, responses, rewards, and log probabilities into an experience buffer. The trainers consume that buffer and ship updated weights back. This is the shape that frameworks like OpenRLHF and TRL with DeepSpeed actually use. A natural question: why 3 separate phases instead of one end-to-end system? 4 reasons. Data efficiency: each phase uses a different kind of data so each can specialize. Stability: each phase builds on a solid foundation. Good supervised fine-tuning gives the reward model sensible outputs to judge, and a stable reward model gives PPO a steady signal. Modularity: you can improve one phase without touching the others. And debugging: if the final model is bad, you can isolate which phase went wrong. Decomposition is what makes a messy pipeline tractable. Could you skip supervised fine-tuning entirely? Yes, and DeepSeek showed it. Their R10 model applied reinforcement learning directly to a base model, and reasoning genuinely emerged. Chain of thought appeared on its own. But the outputs had formatting problems, language mixing, and readability issues. The version trained with supervised fine-tuning first was much cleaner on every front. The lesson: supervised fine-tuning teaches the format of a good response, and reinforcement learning then optimizes within that format. Without it, reinforcement learning has to discover both format and content at once, which is harder. Could you skip the reward model and PPO? Yes, that is direct preference optimization, DPO. Instead of training a reward model and then running PPO, DPO optimizes the policy straight from preference data, treating the language model itself as an implicit reward model. Its loss comes from the closed-form solution to the KL regularized RLHF objective. DPO is simpler and more stable, no 4-model problem, no reinforcement learning instabilities. But PPO can explore beyond the fixed preference data and improve iteratively, which DPO, being offline, cannot. That online versus offline distinction is the crux of the comparison, and DPO is the next sprint. In a Frontier Lab interview, this whole notebook is often a 45-minute deep dive, especially for alignment and post-training roles. The flow is predictable. First, walk through all 3 phases clearly, that is the warm-up. Then a deep dive into whichever phase your answer was thinnest on. Then the diagnostic, something went wrong, here are the symptoms, diagnose it. And finally alternatives, when would you use DPO instead? The single most important follow-up is reward going up while human quality goes down. And the right word for that is reward hacking, or over-optimization. The thing that separates senior from principal answers is fluency across the whole landscape, not just classic RLHF. DPO removes the reward model and PPO. GRPO removes the value model. Iterative or online DPO generates fresh responses, collects new preferences and retrains, getting the best of both worlds. Rejection sampling, or best of N, just samples several responses, keeps the highest scoring and fine-tunes on it. Llama 3 famously used supervised fine-tuning plus rejection sampling plus DPO, with no PPO at all. Being able to compare these trade-offs out loud is what reads as deep understanding. And the production reality behind the tidy 3-phase diagram. Real RLHF is iterative, multiple rounds, each retraining the reward model on the improved policy's outputs. A single iteration on a large model can mean hundreds to over 1,000 high-end GPUs, 1 to 2 weeks for the PPO phase alone, and the dominant cost is not even compute, it is human preference annotation, which can run into the millions per round. The hardest unsolved problem is knowing when to stop. Automated metrics are necessary, but human evaluation remains the gold standard. That gap between the textbook and the real pipeline is itself a great interview topic. So here is what you can now do. You can walk the entire RLHF pipeline end to end, supervised fine-tuning, reward modeling with the Bradley-Terry loss, and PPO with its KL leash and 4 models in memory. You can read the training curves, diagnose reward hacking, mode collapse and KL explosion, and speak to scaling, memory, and the generation bottleneck. And you can compare it fluently to DPO and the rest of the landscape. That is the core of how frontier models are aligned. Follow along on the frontier path, where Moot studies the machine learning interview in the open.